Welcome to the Deep Dive, your shortcut to being truly well-informed. Today, we're diving into a challenge that, well, it probably keeps risk managers like you up at night. Money laundering. This isn't just some, clandestine activity. It's a monumental global problem. We're talking maybe 2% to 5% of the world's GDP annually.
That's enormous.
And for you, working in financial institutions, this translates into direct threats to your institution's stability, potentially significant financial losses.
Absolutely.
And that constant pressure of stringent regulatory requirements. Get it wrong, and you're looking at severe penalties, maybe even losing your license or just massive fines.
It's a relentless fight, really. The UNODC definition is pretty clear, disguising the illegal origin of criminal proceeds, but actually spotting it. That's inherently difficult.
Because they try to look legitimate.
Exactly. Perpetrators mimic legitimate financial behaviors. Sometimes accounts lie dormant for years, then suddenly spring into action for illicit ends. And adding to that complexity, the patterns themselves are constantly evolving. Public policies shift, other environmental factors change.
So the old detection strategies get stale fast.
Very quickly obsolete, yeah.
So we're essentially battling this moving target, and the stakes are incredibly high. Which brings us to the problem with current methods. A lot of institutions rely on dedicated teams, sure, but also these automated rule-based systems.
Right, those systems built on expert knowledge of past fraud patterns.
And they do have their place. They offer explicit audits, explainability, which you absolutely need for compliance.
True.
But they suffer from some really profound limitations. I mean, the numbers are kind of staggering. We're talking 95% to 98% false positives.
Think about that. Just pause on that number. It means a massive, massive drain on your resources. Your teams are investigating countless legitimate transactions. It makes pinpointing the actual high-risk cases incredibly difficult.
It's like, what was the analogy? Finding a tiny fish when 95% of your net is just seaweed?
Pretty much. And those hard-coded thresholds in the rule-based systems, they are so difficult to update in real time.
Why is that? Just bureaucracy?
Well, partly. It's often the inherent inertia you find in large financial institutions. They just can't adapt quickly enough to keep up with the threat as it changes.
That 95% false positive rate, it really does sound debilitating. Why haven't institutions, managed to crack that nut more effectively until now? Is it just that refining rules is that hard? Or is there something fundamentally limited about the whole rule-based idea?
It's a bit of both, I'd say. Refining rules is difficult, time-consuming, but the deeper issue, rule-based systems are fundamentally backward-looking.
Right. They react to what they already know.
Exactly. They react to known patterns. They really struggle with novel schemes, things they haven't seen before. Plus, they depend so heavily on human expertise to design and update them, and that just doesn't scale well with the sheer volume and, frankly, the complexity of modern financial data.
Okay, so that sets the stage. Which brings us to our mission for this deep dive. Giving you a shortcut to understanding a potentially groundbreaking new approach. We're going to unpack a really cutting-edge paper. It's by Harold Gueneau, Alain Celisse, and Pascal Delange, published just recently, July 15th, 2025.
Very fresh research.
And it introduces a novel procedure using advanced AI to try and tackle these challenges head-on. So if we're talking a whole new approach, let's first really dig into why business as usual isn't cutting it. We touched on rules, but what about traditional machine learning? One fundamental flaw seems to be relying on aggregated data.
Yes, that's a big one. You take all that rich, raw transaction data, and you essentially squash it into these macroscopic features, things like transaction totals over a month or counts, averages.
And what gets lost in that squashing?
A tremendous amount of valuable information. Think about it. Imagine trying to understand a complex conversation just by looking at the total number of words spoken instead of the actual words and their sequence.
Okay, yeah.
Much of the granular detail, the sequence of transactions, the specific interplay between different attributes that could actually reveal the illicit activity, it just vanishes.
Right.
Plus, designing meaningful aggregates, well, that still requires significant expert knowledge. And it really limits your ability to detect new money laundering patterns as they emerge. You're always playing catch-up.
Which, as you said, is a huge problem given how fast these things evolve.
Exactly.
Okay, so that's the aggregation issue. What about the other core difficulty? This unavoidable data imbalance. It's almost, it feels strange to say, but it's almost a good problem. To have that fraud is rare, right?
In a sense, yes. But for billing detection models, it creates this massive headache.
It's like trying to teach an AI to spot that needle in a haystack when you've barely got any needles to show it in the first place.
That's a perfect analogy. More crucially, the proportion of fraudulent transactions is, thankfully, very low compared to legal ones. So you get this highly imbalanced data set. For instance, the real-life data set used in the research we're discussing today. The training set had 27% fraudsters, which is actually quite high for this field, surprisingly.
Right.
But the test set, which better reflects real-world conditions, only 5% fraudulent companies.
Wow, okay.
And that extreme imbalance makes traditional supervised learning approaches, where you explicitly teach the model with labeled examples, extremely challenging for you as a financial institution trying to spot real threats in that sea of legitimate activity.
So, okay, we've got a clear picture. Losing critical detail through aggregation, and a desperate lack of labeled fraud cases to learn from. It really does sound like an intractable challenge for financial institutions. How does this paper even start to propose a solution to problems that seem so deep-seated?
Yeah, this is where it gets really innovative. The paper introduces what they call a new frontier, leveraging something called transformers and contrastive learning.
Okay.
The big breakthrough is tackling that aggregation limitation head-on. They consider the whole set of raw transactions collected over time, not aggregates.
The raw stream of data.
Exactly.
Yeah.
And it does this using a transformer neural network. This is an incredibly powerful AI architecture, actually first developed for understanding human language, NLP.
Okay, that might sound a bit counterintuitive. Using an AI for language on financial transactions, what's the link there?
It's actually a really insightful analogy. Think of financial transactions not as isolated numbers, but as a kind of time series of events, almost like a conversation between accounts, if you like.
A conversation, okay.
Each transaction isn't just an amount. It's described by a whole vector of features, some quantitative like amount or value, sure, but also qualitative things. Direction of payment, type, country of the counterparty, maybe even keywords in a description field.
Right, there's a lot of metadata.
A ton. This creates a vast vocabulary of feature combinations and transformers. They are uniquely suited to capture these complex patterns and, crucially, their context over time.
So it's not just about the individual transaction, but the sequence, the context, the story the transactions tell together over time.
That's excellent.
And that's where this key advantage of transformers comes in their ability to capture long-range dependencies. They have this thing called a self-attention mechanism. Why is that so vital for catching money laundering?
Because the really sophisticated fraudulent patterns, they can be operated very subtly over extended periods, months, sometimes even years. Think of it like trying to solve a really complex mystery novel, right?
Yeah.
Where the vital clue was dropped maybe almost invisibly 3 chapters ago.
We just need to connect the dots way back.
Exactly. Traditional models like RNNs or LSTMs, they can struggle with that. They might forget that earlier clue. Transformers, on the other hand, can effectively see and connect these patterns across vast stretches of time. That's exactly what you need to spot these complex, drawn-out money laundering schemes.
Plus, you mentioned they're more efficient.
Yeah, compared to some older sequence models, they often have lower computational complexity and are easier to parallelize, which is crucial when you're dealing with the sheer volume of financial data you have to process daily.
Okay, that tackles the raw data, the aggregation problem. But what about the other big hurdle we talked about, the lack of labels? The scarcity problem.
Right.
Given how hard it is to get reliable, labeled money laundering data, how on earth do you train such a powerful, complex model like a transformer without tons of pre-labeled fraud examples?
That is the million-dollar question, isn't it? And this is where the second key piece comes in. Contrastive learning.
Contrastive learning, okay.
It's a type of self-supervised learning, or SSL, which basically means it trains the model without exploiting any explicit fraud labels.
How does that even work?
Right.
Learning without knowing the answer.
The core idea is actually brilliantly simple, but very powerful. You learn robust representations, those fingerprints we talked about, by essentially teaching the model to figure out which observations are similar to each other and push them closer together in this kind of simplified conceptual map or latent space.
Okay.
While at the same time pulling dissimilar observations further apart.
So when you say simplified conceptual space, just for our listeners who might not be deep in the AI weeds, how can we visualize that? Is it like boiling down all the complexity into a point on a map?
That's a great way to put it. Imagine all the intricate details of a bank account, every single transaction, every subtle pattern over months being condensed into a unique fingerprint. Or, yeah, a single point on a simplified map. That's the latent space.
And on this map, Similar accounts cluster together.
Exactly. This map allows accounts with similar underlying behaviors to naturally cluster together. This makes it easier for the AI to sort of see relationships and similarities that were completely hidden in the raw, complex, high-dimensional data.
Okay, so the AI is learning to spot these subtle resemblances, essentially teaching itself what normal or similar financial behavior looks like, even though we haven't explicitly told it this is fraud, this is not. How does it know which accounts are supposed to be similar, though?
Ah, good question. It doesn't use the fraud labels. Instead, it defines similarity based on other, more readily available auxiliary data. Think high-level customer descriptors that you already have, things like their legal form, their industry sector, maybe geographical information.
So it assumes, for example, that two small retail businesses in the same city should probably look more similar in their transaction patterns than, say, one of those businesses in a large multinational corporation.
Precisely. It uses these kinds of heuristics from the auxiliary data, they call it D in the paper, to guide the learning process. The transformer first acts as an encoder, taking the raw transaction time series and mapping it into that initial finite dimensional fingerprint or embedding.
Right.
Then there's usually a projection head, often a simpler network like a multi-layer perceptron, that projects this fingerprint into an even lower dimensional space. This helps improve generalization and reduces computational cost.
Okay.
And to make this learning really effective, especially with potentially limited examples, they use a couple of clever tricks. One is a memory bank.
A memory bank.
Yeah, it basically stores embeddings from past batches of data. This increases the diversity of examples the model compares against, both positive ones it should be similar to and negative ones it should be different from. It helps stabilize the learning.
Makes sense. More comparisons, better learning.
And another novel aspect here is injecting a tiny bit of Gaussian noise. But interestingly, they inject it into the latent space, that projected fingerprint space, not directly into the raw time series data.
Okay, adding noise. That sounds counterintuitive again. Why make the fingerprints fuzzier?
Yeah, it does seem odd. But think about it like this. Imagine you're teaching a child to recognize a cat. You don't just show them one perfect high-res photo against a white background.
Right, you show them different cats, different angles.
Exactly. Cats partly hidden, cats in weird lighting, maybe slightly blurry photos. That little bit of noise or variation forces the child or the AI to learn the essential features of catness, not just memorize one specific image.
Ah, I see. So it helps the model generalize better.
Precisely. It acts as a regularizer, prevents the model from overfitting to the specific data it's seen, helps it explore slightly different situations, and crucially, it also seems to help remedy that strong class imbalance between fraudsters and non-fraudsters we talked about.
Okay, that makes sense. And how is this all optimized? What tells the model it's doing a good job?
It's optimized using a specific loss function called info-NC. Basically, it mathematically encourages the model to maximize the similarity score between a reference observation and its positive similar examples, while simultaneously minimizing the similarity score to all the negative dissimilar examples in the batch or memory bank. There's also a temperature parameter that sort of scales this optimization.
Okay, wow. So that's the unsupervised pre-training using contrastive learning. Once this sophisticated transformer has learned to produce these rich, generic representations of financial behavior, what's the next step? How do we actually use this to detect money laundering?
Right, so that's the second stage, the downstream classification task. Now that we have these powerful self-learned representations or embeddings.
The fingerprints.
Yeah, the fingerprints. Yeah. We feed those into a much simpler classifier, like a standard logistic regression model. This classifier is trained using the limited available fraud labels you have.
Ah, okay. So the labels come in here.
Yes. The heavy lifting of understanding the complex patterns is done by the pre-trained transformer, unsupervised. Then, the simpler classifier learns to map those rich fingerprints to the actual outcome. Fraudster or non-fraudster, it outputs a score, basically, a probability of that account being fraudulent.
So you're combining the best of both worlds. The deep pattern recognition of the transformer, trained without needing many labels, and then a targeted, supervised step using the labels you do have.
Exactly. Sometimes they might even fine-tune the transformer slightly during the supervised stage, but the core idea is leveraging that powerful pre-trained representation.
But thinking back to the operational challenges for risk managers, that severe class imbalance, the crippling cost of false positives, just getting a probability score, is that enough? How does this new procedure help manage that investigation workload?
That's a critical point, and the paper introduces a really neat solution for practical application. A two-threshold classification approach.
Two thresholds, not just one cutoff.
No. It's designed specifically for operational efficiency in your daily work. Instead of a single point where you say, above this is suspicious, below is not, they use two distinct thresholds. A low threshold, TL, and a high threshold, TH.
Okay, what's the low threshold for?
TL is designed to efficiently discard the observations that are almost certainly not suspicious. Any account scoring below this low threshold is confidently declared non-fraudulent.
Ah, so you can just clear those off the investigation list immediately.
Exactly. This is potentially a huge game changer. It removes a massive chunk of legitimate accounts from your analyst queues right away, saving immense time and resources. No more wasting effort on the obviously clean accounts.
Okay, that sounds incredibly useful. And the high threshold TH, that must be for catching the really bad actors.
Precisely. TA focuses on identifying the most suspicious observations. Accounts scoring above this high threshold are flagged as high-priority potential fraudsters. These are the ones you want your expert investigators focusing on immediately.
So it's a triage system, essentially. Clear the definite negatives, flag the definite positives, and maybe leave a gray area in between.
Well, the accounts between TL and T might still warrant some level of review, perhaps automated checks, or a lower priority investigation. But the key is the clear separation at both ends. It allows your teams to focus their human expertise where it's most valuable on those high-probability cases flagged by TL.
What's really fascinating, though, is how they set these thresholds. The paper mentions it's not just picking numbers out of thin air or doing a simple top Greek ranking, which, as you know, gives you no real guarantee on how many false positives you're getting in that top group.
Right. Ad hoc methods are problematic.
Instead, they leverage a statistical method, the 𝘁𝗵𝗎-Hochberg-BH procedure.
Yes, and this is huge for practical implementation and regulatory acceptance.
Why is BH so important here?
Because the 𝘁𝗵𝗎-Hochberg procedure allows you to control the false discovery rate, FDR, at a prescribed level that you choose beforehand.
False discovery rate. Remind us what that means practically.
FDR is the expected proportion of false positives among the cases you flagged as suspicious. So if you set your target FDR at, say, 10% for the high threshold, the BH procedure helps you find the specific threshold T such that among all the accounts scoring above it, you can expect, on average, only 10% of them to be actual false positives, i.e., non-fraudsters.
So you get a statistical guarantee on your precision. If FDR is 10%, precision is 90%.
Exactly. Controlling FDR below level alpha is equivalent to ensuring your precision is greater than 1 alpha. This is paramount for you as risk managers. You're no longer just hoping you catch fraud. You're operating with a statistically guaranteed ceiling on the proportion of false alarms within your flagged set.
That directly tackles that false positive inflation from the rule-based systems.
Absolutely. No more drowning in alerts where 95% are nothing. With BH, you can say, okay, we're setting the high threshold to give us an expected FDR of, say, 20%. We accept that 1 in 5 flagged cases might be benign, but we know we're focusing on a much richer pool of potential fraud.
How does BH actually find these thresholds?
It uses the p-values, estimated from the classification scores, essentially, how likely each account is to be a fraudster or non-fraudster based on the model. It then algorithmically sorts these and finds the cutoff points, which become TL and T8 for the low and high FDR targets respectively, that satisfy the desired FDR levels. It's a robust, data-driven way to control error rates.
So this sounds incredibly powerful, statistically sound, but I can hear some listeners, maybe those wary of black box AI, thinking about explainability. How do you balance this cutting-edge transformer capability with the need for transparency and accountability in financial risk?
That's a really important and valid concern, and I think the two-stage approach helps quite a bit here.
How so?
Well, first, the final classification step often uses a more transparent model, like the logistic regression we mentioned. Its output is a probability score, which is somewhat interpretable. But perhaps more importantly, the 𝘁𝗵𝗎-Hochberg procedure provides that statistical guarantee on your error rate, the FDR.
Ah, so the accountability comes from the statistics, not necessarily from tracing every neuron.
In a way, yes. It provides a very strong form of accountability. It tells you, with a quantified degree of confidence, the expected precision of your detection efforts at both the high and low ends. And often, that's what regulators care deeply about, understanding and controlling the reliability and error rates of your system. Even if the underlying pattern recognition is complex, it's about knowing the performance bounds.
That's a crucial distinction. It's about managing risk through controlled error rates. Okay, theory sounds great. Statistical guarantees are great. But how did this actually perform when they tested it on real data? You mentioned they used a complex, anonymized real-life data set.
Indeed, they did. Each observation, as we said, was a bank account, described by a 3-month time series of financial transactions. Lots of different quantitative and qualitative features in there.
And crucially, that test set had only 5% fraudsters, reflecting the real world.
Right, a very challenging imbalanced scenario.
So what did the results look like? Did those learned fingerprints from the transformer actually manage to separate the fraudsters visually?
They were remarkably clear, actually. When they visualized the embeddings, projecting them onto that simplified 2D map, the transformer's outputs showed a pretty compact cluster of the known fraudsters.
So they grouped together nicely.
Yes, and importantly, this cluster was stable. They ran the training multiple times, and this fraudster cluster consistently appeared. It really demonstrates the transformer's ability to learn these distinct underlying patterns associated with suspicious activity.
And how did that compare to other methods they tested?
Well, in stark contrast, models like an LSTM autoencoder, another sequence model, showed much less clear fraudster clusters, and there was more variability between runs.
Okay.
And perhaps unsurprisingly, models trained only on the traditional aggregated tabular data. They resulted in heavily overlapping distributions. Looking at the map, it was nearly impossible to visually distinguish between the fraudsters and the non-fraudsters.
So the pictures already tell a strong story.
The visual evidence is quite compelling about the transformer's superior pattern recognition, especially with the contrast of pre-training.
Okay, visuals are one thing. Let's get to the hard numbers. How did this translate into actual quantifiable performance improvements? Did it really separate the scores better?
Significantly better. The transformer-based approach, particularly the one using contrastive learning for pre-training, led to much cleaner separation of the fraudster and non-fraudster score distributions.
How so?
Well, the legitimate accounts, the non-fraudsters, were heavily concentrated down at the very low scores. In fact, in their test set, no fraudsters were observed below a score of 0.4.
0 fraudsters below 0.4. That's quite a gap.
It is. And meanwhile, the actual fraudsters showed a much higher concentration up near a score of 1. So you get this much clearer distinction, far fewer ambiguous cases lingering in the middle compared to the other methods. This makes setting those thresholds much more effective for your analysts.
Okay, let's talk about those thresholds in action. First, the high threshold, TREAT, designed to catch the most suspicious cases. What were the detection rates like there?
They set a target false discovery rate, FDRH, of 0.40. So accepting that up to 40% of the flagged accounts might turn out to be false positives, which, remember, is still way better than 95%.
Right.
At that FDR level, the transformer-based approaches specifically, using the embeddings with logistic regression, and also fine-tuning the transformer itself, they detected between 20.34% and 23.02% of the total frauds present in the test set.
Okay, 23% of all fraudsters caught, with a controlled 40% FDR. How does that compare to the baseline methods?
It blows them out of the water. For the same 40% FDR target, logistic regression trained only on the aggregated tabular data. It detected 0% of the frauds.
Zero.
𝘁𝗄𝐺, a more powerful model but still on tabular data, caught only 0.86%. Even using an LSTM's embeddings with logistic regression only got 7.33%.
Wow, so the transformer approach is catching vastly more real fraud for the same acceptable level of false alarm.
Exactly. For you as risk managers, that translates directly into identifying significantly more illicit activity that you might otherwise miss without getting completely overwhelmed by false positives.
That's impressive for catching threats. But what about the other side? The low threshold. PL, the one for eliminating the noise and freeing up resources. This seems like where the big operational win could be.
Absolutely. This is where the efficiency gains really shine for your teams. For the low threshold, they set a very strict false discovery rate, FDRL, of just 0.03.
So aiming to incorrectly discard only 3% of the actual fraudsters.
Precisely, a very conservative level. And at that level, the transformer-based approaches confidently identified and discarded an astounding 96.77% to 97.11% of the true non-fraudsters.
Nearly 97% of the good guys correctly cleared out right away.
Yes. Think about the impact that has on your alert queues. You can potentially remove almost all the non-suspicious accounts automatically. This drastically reduces the volume of unnecessary investigations. It saves huge amounts of time, computational resources.
And lets your expert analysts focus their energy on those high-priority flags from the threshold where their skills are really needed.
That's exactly the idea. It makes the whole process much more targeted and efficient.
So boiling it down, the transformer, especially with that contrastive learning pre-training, seems to consistently deliver superior performance on both ends, identifying more true fraudsters with controlled false positives and confidently dismissing a huge majority of non-fraudsters to reduce workload, all while keeping that critical false discovery rate statistically managed. Okay, let's try and bring this all home. We've walked through quite a journey here. We've seen how this two-step methodology really looks like a significant leap forward in tackling money laundering detection.
It combines several powerful ideas.
You've got the raw power of transformer neural networks, digging into the complex sequences and raw transaction data,
Paired with the cleverness of contrastive learning to get around that huge problem of scarce labeled data.
and then crucially, layering on that adaptive two-threshold strategy, which isn't just guesswork, but precisely calibrated using the Benjamin-Hochberg procedure for statistical control.
And it directly addresses those critical weaknesses of the traditional rule-based systems that you, our listeners, are probably all too familiar with.
Right, the cripplingly high false positive rates, the inability to keep up with evolving fraud patterns.
Yeah, the contrastive learning pre-training gives you those robust representations without needing masses of labels up front. And the two-threshold system, optimized with BH, lets you tune the trade-off between catching fraud and managing workload. It really feels like a fundamental shift.
So for you, listening in your role as a risk manager, what's the bottom line? This means a tangible enhancement in your capabilities, doesn't it?
Absolutely. You can realistically expect to effectively reduce that mountain of unnecessary investigations. That means saving immense amounts of analyst time, saving computational resources.
While at the same time actually improving your ability to detect genuine fraudulent activities, and doing so with a false positive rate that you can control and predict.
Exactly. This kind of framework doesn't just offer a chance to outperform traditional methods. It provides those data-driven statistical guarantees that are becoming increasingly crucial for demonstrating effective risk management and, frankly, for regulatory compliance.
It certainly seems like a compelling direction, which leads us to our final provocative thought for you to take away.
Given what we've seen here, the demonstrated power of AI models like this transformer to distill incredibly complex, unlabeled financial data into actionable insights. Its ability to manage that delicate balance between false positives and true detections, using statistically sound methods like BH. How might integrating these kinds of adaptable cutting-edge frameworks fundamentally reshape the very nature of human financial analysis in AML?
Could it shift the focus entirely away from that manual data sifting and alert clearing
towards much more strategic intelligence-led investigations, where the AI handles the filtering and prioritization, and the human experts focus on the complex cases, the connections, the bigger picture? Something to think about.